Continuous flow reactors. Continuous flow reactors are almost always operated at a steady state. We will consider three types: the continuous stirred tank reactor, CSTR, the flow reactor, PFR, and the packet bed reactor, PBR. The continuous stirred tank reactor. This is normally operated at steady state and is assumed to be perfectly mixed. Consequently, there is no time dependent or position dependent of the temperature, the concentration, or the reaction rate inside the CSTR. That is, every variable is the same at every point inside the reactor. So, here we have a continuous stirred tank reactor. At the top left, we will have the entrance of the reactants, and at the bottom right of the reactor, we have the exit of the product. Inside the reactor, we have system to mix the reactants. The temperature and concentration in the exit stream, our model has been the same as those inside the reactor. And when the general mole balance equation Fj0 minus Fj plus the integral of Rj dV equal to dnj divided by dt is applied to a CSTR operated at steady state, we know that dnj divided by dt is equal to 0 because it's a flow reactor and there is no accumulation. In this case, there are no special variation in the rate of reaction. That means that it's perfectly mixed all the reactants inside the reactor. In that case, the integral of Rj dV it becomes equal to Rj times B because the rate is constant, so we can take it out of the integral. So this equation takes the familiar form known as the design equation for a CSTR, which is equal the volume equal to Fj0 minus Fj, all that divided by minus Rj. The CSTR equation gives the reactor volume B necessary to reduce the entering flow rate of species J from Fj0 to the exit flow rate Fj, when species J is disappearing at a rate of minus Rj. The molar flow rate Fj is just the product of the concentration of species J and the volumetric flow rate B. So Fj is equal to Cj times B. In the left we have moles divided by units of time. In the right, the concentration is in moles divided by volume, and the volumetric flow rate is volume divided by time. So at the end we will have in both sides mole divided by time. Consequently, we could obtain the equations, we could combine, the equations on right and balance on species A as the volume is equal to the volumetric flow rate at the entrance V0 times the concentration of A at the entrance Ci0 minus the volumetric flow rate at the exit B times the concentration of A at the exit, all that divided by minus Ra.